Thank you. Thank you very much. Thank you very much to the organizer for the opportunity to give a talk. So I want to talk today about virtual rigid motif of definable sets in valued fields. And as a motivation for what I want to do, I will start with an old question by Grothendieck that is now well understood, and there are many different answers. So the question is the following. So he asks to construct a ring morphism from the Grothendieck group of varieties. So I formulate the question anachronically, but that's what it is called now, the Grothendieck group of varieties over a field K to the Grothendieck group of motives over K. And so for him, so he asks this in a letter to Serre, and he mentions that he thinks that there should be a theory of motives that should satisfy that and this and that properties, and that we should try to build a map like this, maybe to investigate some properties of the motif. So yeah, I will also just fix one for all little k, an algebraically closed field of characteristic 0, and big K will be the field of Laurent series over little k. And my goal today will be to formulate and prove an analogous of this question, but for valued fields. So my goal to construct a ring morphism from what I will call the Grothendieck group of VF big K to the Grothendieck group of Widget motifs over big K. So I will explain a little bit later what kind of motifs I'm considering. And here, VFK will be the category of definable set in ACVF with parameter in big K, or maybe in the Lipschitz expansion of this theory with analytic functions. And of course, I could define a zero morphism, but that would not be very interesting. So in particular, I will ask this morphism to be compatible with the algebraic morphism. So you can formulate the same question with, in place of little k, big K, and I want to have compatibilities between the two morphisms. And so let me, to be concrete, maybe it has been, the Grothendieck group of variety has been defined only once in this conference. So I can probably redefine it so everybody knows what I'm talking about. And also what I mean by Grothendieck group of a definable set in some theory. So oh, and sorry, I should have mentioned that this question to construct such a morphism has been asked by Ayoub Ivor Sebag, and it is in relation with the, it will have some application to the analytic Miller fiber, but I will come to that at the end of the talk. So Grothendieck group. So the most classical kind of Grothendieck groups we can think of is the Grothendieck group of varieties. So K via K, and let me recall you that is the free abelian group generated by isomorphism classes of varieties with relations with so-called the cut and pass relations, that the class of X is the class of Y plus the class of U if Y is a closed subvariety of X and U the open complement. And we get a ring structure just induced by the Cartesian product. The unit is just the class of a point. And we can also do relative versions. So consider the class of Grothendieck group of varieties over some varieties S. And we can also do some an equivalent version that I will need at some point. And I will denote by that the Grothendieck group of varieties with a mu hat action, and where mu hat is the group of roots of unity. And so I consider varieties, I start by isomorphism classes of varieties with some good mu hat action. And by that, I mean that the action factors through some mu n, where mu n is a group of nth roots of unity. And I also put some scissors relation when I ask to get the relation is that the action of mu hat on X restricts to an action on Y and U. Okay. But we can also define Grothendieck group of theories. So let if I take a T and L theory, I can define Grothendieck group of T is so the same thing, the free abelian group generated by isomorphism classes of L formulas. So I denote by them a class of phi. And by isomorphism, I mean just if T proves that phi is equals to psi, then class of phi is equal to class of phi. And I put some relations. My relations are just that if I have some, that the class of phi and psi is the sum of the two classes, provided that the intersection is empty. And from this, just for example, by so we can remark that, and so in particular, I mean phi formula really without parameters, and so the remark is that the Grothendieck group of AC, let's say of ACF over some field F, is isomorphic to the Grothendieck group of varieties over F for F field of characteristic 0. And so that's an example. And the other example I will use is Grothendieck group of ACVF K. So definable sets in the theory of algebraically closed valued fields with parameter in big K, the field of Lorentz series. And I will, so here I'm really working with just a one-sorted language, and just to be shorter, I will just denote this by VFK. And but I could also consider the Grothendieck group of ACVF AN, so the expansion with by Lipschitz, where we had restricted analytic functions, and it is a consequences of Hrushovski and Kazhdan theory of motivic integration that their Grothendieck groups are isomorphic. AC. And okay, so that's explaining a part of the question. And now I should move on to motives. So I won't define, I will tell you what category of motive I'm considering. I won't define precisely exactly what it is, but I will try to give you some properties of the category so that that will be useful for me. So I will use denote the category of motive I'm using by dA of K. So it is the derived stable A1 invariant Q-linear motives. So it is defined by Ayoub. Modifying a bit a definition by following a definition by Morel-Wojcicki of a very similar category. So how should you think about this category? So the point is that if I take X a variety over K, I get two motives in D of K, something called, I will denote M K of X, it's homological motive. And the cohomological motive. And you can think of the homological motive of X as a kind of universal homology for X. And for example, knowing the homological motive of X, you will know all the homology groups of X in any reasonable homology theory. And so some more, so maybe I can explain at least the notation. So D is for derived. D. So it doesn't mean that it is really a derived category, but for me here, it will mean that dA of K is a triangulated category. So in particular, I have a distinguished class of triangles, and you can think of those triangles are kind of analogous of long exact sequence in homology or cohomology. And the A is for A1 invariant. And by this, I mean that the motive of A1 of A of X is always isomorphic to the motive of X. So this property, which is true in any reasonable, in any homology theory, is in fact imposed in the construction of the category, and is really very important. Okay, and so from this, as I said, as soon as you know the motive, you know, for example, if K is C, you will know the Betti cohomology of X. And it is formally formally, it is just that we say that we have some realization maps from the category of motifs to various categories. So just an example. So for example, if we take K to be C, we have the Betty realization. So it will be just a functor, let's say HBT, from the of C to quoted vector spaces, Q vector spaces, and it sends the homological motive of X, of the variety X, to the direction of all the Betty cohomology group of XC. So if you want, you can just think of motifs that are kind of really homology theory or cohomology theory. Okay, and an important theorem on this category, which was proven by Ayoub, is the existence of a six-functor formalism. So, and there is and by this I mean that you can also define motifs over any base S, and if you have a morphism between, let's say, X and Y, you will get some push forward and pullbacks between the categories. And the six-functor formalism is that you can also define some Schwick functors, and just the only consequence of this I will need is that, in particular, we get a notion of cohomological motive with compact support. And we'll denote by this by M, so cohomological motive with compact support. And if, so for example, if X is smooth, then we have an easy formula for the motive with compact support. It's just the motive of X with some twists minus so here in parentheses, I mean it's an iteration of the Tate twist. So it's really the analogous of the Tate twist in étale cohomology, for example, but it also appears here. And here, the shift is just the shift by the suspension functor we get because the category is triangulated. And so you say that it's not so hard to guess, and it's easy to show that I mean, you can define this for any smooth varieties, but the complicated part is shows that there are some compatibilities between the motive with compact support, and that's part of the six-functor formalism. But from this, and in some sense it is really designed to be true, we can very easily define a map, answer Grothendieck's question, just by sending a class of a variety to the class of its cohomological motive with compact support. we can define a ring morphism from the Grothendieck group of varieties to the Grothendieck group of motives by sending the class of a variety to the class of its cohomological motive with compact support. And I should tell you what I mean by Grothendieck group of this category, where so as before, it's defined isomorphism free abelian group generated by isomorphism classes of constructible motive. So by constructible motive, I just mean motives of varieties or their twist or their shift and with relations. That if I have a distinguished triangle, so A to B to C, I say that the class of B is the class of A plus the class of C. And the fact that this map satisfies, so that this map is well defined, it just means that as soon as I get, I take a variety X and Y, so a closed subvariety, I will get an exact triangle between the class, the cohomological motive with compact support of X, of Y, and of U, and that's part of the six-functor formalism. So it's really the direct corollary, which was first used by Ivora and Sebag. But that's not the first answer to Grothendieck's question. It was in a slightly different context, using a different category of motives, but it was also defined by Gilles Soulet, Guylaine Navarro-Aznar, and then with completely different techniques by Bittner. Okay, and from this, we can also define, we can also consider widget motives. So as I've not defined motives, I won't define a widget motive either, but you can think of them are let K dA of K, the category of motives of K of rigid analytic K-varieties. So it was defined by Ayoub. And the idea is you do the same as the definition of the category of motives, but instead of starting with K-varieties, you start with rigid analytic K-varieties. So here is the sense of state, but you could also start with a category of Berkovich spaces or adic spaces. You would probably get the same category at the end. Okay, and so now I can, where do I want to state it? I can state the main theorem. Yeah.
Question: if you restrict, if you consider a full subcategory with objects that are unifications.
Yeah, yeah. Yeah, you get, and there is a map, there is a functor from dA of big K on to K dA of K, and it's just induced by an identification. So for example, if I have the motive of X, I will send it to the motive of, so maybe I should put a weak here, of the analytification of X. Yes. Okay. So the theorem is the following, that there is a unique rigomorphism from the Grothendieck group of definable set in ACVF to the Grothendieck group of rigid motives characterized by the following condition. If I take a smooth quasi-compact connected rigid analytic varieties X, K-variety X of dimension D, then K-rig of the class of X is just the rigid motive of X with some twist. And so it's not so hard to show that such classes generate the full Grothendieck group of VF. But it's much more complicated to show that this assignment is well defined. Yes, it is well defined. It doesn't depend on the choices when you cut your definable sets in such pieces. But to show that it is well defined, I will need to use Hrushovski and Kazhdan's theory of motivic integration, and it is this use is okay. Yeah, no, sorry. I also wanted to say that it's also not so from the algebraic description of the algebraic version of the Whig morphism, the ecological motive with compact support was for X smooth of this form. So the suspension factor doesn't appear because in the Grothendieck group it's just the identity. And so I just took an analogous of the definition of ecological motive with compact support, and with this condition that you also only work with quasi-compact varieties. If you remove quasi-compact, it will be false. For some quasi-compact varieties, this formula doesn't work. But it's also good because just from this condition, if you apply that to X and analytification of smooth projective varieties, you will see that this morphism is compatible with the algebraic one through the analytification factor. And so it's indeed something you can consider that a kind of virtual notion of cosmological motif with compact support. And so there is also some commutative diagram that resumes the whole situation. And so you can start with Grothendieck of a variety of a big K. You can go to VFK. Here you can take the algebraic morphism, dA. Okay. Here, just the analytification, 2K rig. Here, that's the morphism K-rid I just constructed. And the diagram will explain you how you can define it very easily. But what's not so easy, it's maybe to check the condition I ask. So in fact, by Hrushovski and Kazhdan theory of motivic integration, we get a morphism. I will talk a bit more about it later. Vol from KVFK to Grothendieck group of varieties with some mu hat action. And you can also forget the action if you want. And down there, you can apply key little k. And here you can define, I won't explain too much about it, but talk too much about it, but you can also define an equivariant version of this map, kk, just taking into account the mu hat action. And I denote that by key mu hat, and it lands in, so for technical reasons, it's not technically defined as a category of motives with some mu hat action. It's so-called the category of quasi-unipotent motives, but you should really think of this category of motive with some mu hat action. And so this commutativity is just you forget the mu hat action. And in fact, you can, from this category of quasi-unipotent motive, you can very easily goes up, but in fact here we have an isomorphism, and that's the thing I want to explain now. But as soon as so let's assume that key mu hat is just a version of this with the action. So I won't talk more about it, and we just define this map, and talk after about define a bit the Hrushovski and Kazhdan motivic integration morphism. So the quasi-unipotent motive are defined as a subcategory of the motives over GM. And in fact, you can also more or less do the same thing with Grothendieck group of varieties with mu hat action. You can view it in some sense at the sub-wing of the Grothendieck group of varieties over GM. But from GM, you can just bait change to go to motive over big K, just because GM is spec of K bracket T, T minus 1, and you set this T to the T of, because let me remind you that K is K double bracket T, so you send T to T. So it's define you a functor, and then you take the analytification. And you land in rig dA. Okay. And if you define, you call big F this the composition, and a theorem by Ayoub is that big F is an equivalence of category. Okay, so up there, the map is really an isomorphism. And the last thing I need to define a bit is the morphism vol. So it is, I mean, it doesn't look like much motivic integration, but in fact, it is really close to a morphism of motivic integration, just that we do integration without volume form. So it looks like a bit strange, but you can, in fact, upgrade it to take into account some volume forms, and then it really looks like motivic integration. But it is so. So I won't really explain you how it is defined. I will just tell you the theorem. So it tells you how it defines precisely the map, but I won't show you how it is actually built. So here's the theorem. There is a unique ring morphism, vol from K VFK to Grothendieck group of variety with some mu action. And the fact that some mu action appears should not be too surprising, since mu just appears as the Galois group of big K. So in fact, definable sets in VK K are endowed with some mu action, and the morphism we call doesn't forget the action. And so what are the conditions? Is that first, if I take delta some definable set, so gamma is a value group sort, and I take some delta some definable set, then I can take the preimage of delta by the valuation. So it gives me a definable set in the VF sort, and I can take its class. And I said that vol of this class is just the bounded Euler characteristic of delta times the class of GM K to the power n. And here, so gamma, the index structure on gamma is O-minimal, so we get the usual O-minimal Euler characteristic. And bounded means that I intersect delta with some big boxes, with some big closed box. And if the radius of the box is big enough, then the Euler characteristic stabilizes, and it defines me something. So, and it is well defined only because I don't have multiplication of gamma. The structure of gamma is just ordered abelian group, dense, and so this defines something consistent. And the other kind of classes I impose are the following: if I take x some variety over k, smooth, and I take r some positive integer, and f a non-vanishing function on x, then I can look at the class to the following definable set. Y will be the point yu in x o. Okay, so in the valuation ring of algebraically of k, times k, so that u is an rth root of the function t times f of y. So I can look at this definable set, and I'm requiring that the volume of such class is just the class of x, where I add some roots of f also, such as you have for f. And I see this as a variety with some action of mu r. And where the action of mu r is just on the variable u. And so I can take the class of this in mu hat. And so it's, once again, it's not so hard to show that such classes generate the whole Grothendieck ring of K VFK. But what's much more complicated is to show that it is well defined. And the way Hrushovski and Kazhdan prove the theorem is a bit similar to the definition of Ayoub of the equivalence to this functor. In fact, they really work in the theory of CVF with the RV sorts, and they start by looking at the definable set in RV, and they lift it, and they show that the map they define is surjective, and they study the kernel, and the kernel is really very simple, and that allows them to define a map in the other way around. And then to get actually vol, you get somehow you get rid of the value group by applying a kind of this bounded Euler characteristic to really land in the Grothendieck group of varieties with muat action. Okay, so that's explained more or less the theorem. I mean, everything is defined now, so you can see that to define the ring morphism K-rig, you just compose vol with K muat and then this F here. So you don't need the theorem by Ayoub to define the map. But then I need to show by using some semi-stable models that the condition written here is indeed realized, satisfied. Okay, in the last few minutes, I will just mention some few applications. So I won't get into details, but there is also some kind of duality theorem that implies a kind of, so that characterized K-rig for classes of varieties that appears are tube over quasi-compact over projective varieties. But I'm not going to explain this in details. Just let me mention that there is a kind of Poincaré duality statement. That is, if I take X some smooth and proper K, so if I take the originality K-varieties that is smooth and proper, then it's cohomological motive with its cohomological rigid motive. At least the class of its cohomological rigid motive will be equal to the class of its homological rigid motive twisted by the dimension. Proper connected of dimension D. So it's really a kind of virtual Poincaré duality. And I also, from the proof of the theorem, one can show that one sees that vol of what I will denote f and fx is equal to psi fx, where psi fx is a Denef-Lozer Milnor fiber, motivic Milnor fiber. And here it's Nikas-Sebag analytic Milnor fiber. No. And it was also shown by Nikas and Payne, and Nikas, Payne, and Schroeter without taking into account the muat action, and with more or less some similar techniques. But from this fact, okay, we can deduce something else, which was the initial motivation for this work. Okay, I think I should at least define what the analytic Miller fiber is, at least the rational point of it. Just the point y in the evaluation ring, such that f of y is equal to t, and if you take the residue of y, you get x. And so that's for f, a polynomial with coefficient in little k, and x in a 0 of f. And so so you can put a structure of rigid analytic varieties on this set also. And it was studied by Sebag, and they show that we can recover the cohomology of the Miller fiber from its cohomology. And from the, not specifically from the Poincaré duality theorem, but from a similar computation, I can show that if I take Keyrig of this analytic Miller fiber, I get the rigid cohomological motive of the analytic Miller fiber. And so, but so now if I combine this observation with the one above, that the vol of the analytic Miller fiber gives you the Denef-Loser Miller fiber, and I look at the commutative diagram up there, I see that if I apply the Ayoub equivalence between rigid motives and the quasi-unipotent motive, so let me denote R the inverse of or let's just set, I think it was f minus 1 of the cohomological motive of the analytic Miller fiber is equal to the image by Kim hat of the Denef-Loser motivic Miller fiber. And so this equality is in Q in quasi-unipotent motive. Sorry, in quasi-unipotent motives, Grothendieck group of quasi-unipotent motive. And in particular, if we forget the mu-hat action, we get the same thing. So I think okay, I don't put some name, maybe I should. Just the functors that forget the action from QDA to GA, I denote that by 1 star. But it's not so important. So the name. And I see that this kk of and in fact this fact, so I get the same thing but without action. And this fact was proven by Ayoub Sebag. Proven. And in their paper, they ask if you could define a morphism of the form of Keyrig to recover this fact and maybe upgrade it to the equivalence level. So that is done now. And thank you for your attention.